Hello everyone. So, let us continue our discussion. We are in week 2 and this is our first lecture. Okay, so we have already discussed stress, right, and how a material, elastic material behaves under the action of force. And we have talked about two different stresses. One is called normal stress and the second one is shear stress. Okay, so if we take the same example that we considered in our last class and solve some problem, that we have bar which is having a load of P at the ends, right, and this is the gauge length. Okay. For the time being, gauge length is not important. Now, obviously, our assumption was that this force P acting uniformly over the cross section, right. So, that is the case. Now, if we consider say a plane and let us consider the left half and draw the free body diagram. So, we have the left half and at this section there will be a resultant force. We do not know the direction yet, but that is not important for the time being. Say this is T. The remaining half, if I just complete the section, is where we have the force P at the right end and then we have force T which is in opposite direction acts, right. Now, if we connect these two, obviously, the reaction force will get cancelled and that is how we will get back the original force configuration. Now, if we consider a small element here, and then if we study the component of stresses acting on this section. So, this plane will be defined by the normal. So, this is the normal. Obviously, we can resolve this T along this normal and perpendicular to the normal, right. The one along the normal is the normal stress sigma n. Obviously, we consider the force over unit cross section and that is how I write it. Otherwise, we can also write it in terms of force. So, this will be say T n and then this is T r. Obviously, T square is equal to T r square plus T n square. So, what we can see is that the moment we take a cross section and consider a differential element, then we get two components, one along the perpendicular and the other one along the plane itself. Now, if we draw the free body diagram of this differential element, what we have? This is say x direction and this is the y direction. So, the size of this element is delta x delta y. And if we consider unit thickness, and then we can draw the stresses acting. So, we will have sigma, that is the normal component, and then we will have tau. Obviously, on the opposite face we will have again sigma, and then we can easily draw the shear stress tau. We will come to the remaining two faces, but before that let us complete the nomenclature, because when we deal with stress, it has two important aspects. One is the plane over which it is acting. So, if we talk about this sigma, obviously it is acting over a plane which is defined by the normal. So, this is the normal x, right. So, the sigma is acting over x plane. So, we will use the subscript x to denote the plane over which it is acting, and on top of that it has a particular direction. In this case it is acting towards positive x. So, we will call it sigma xx. If I follow the same nomenclature, tau is acting over x, but it is along the direction of y. So, we call it tau xy. And then now let us complete the other two faces. So, there will be a normal stress. So, this will be sigma acting over y plane along the direction of y. So, we call it sigma yy. And then we will have tau yx. Let me just erase these two, otherwise there will be no space for writing further. But we can understand that on each phase we have normal stress. So, in this case we have normal stress sigma xx, sigma yy, and then we have shear stress which is tau xy and tau yx. And we have also derived that tau xy is equal to tau yx, right. Their magnitude are same. So, we can modify this with tau xy. Okay. Now, here also we have xx, and then let me write here tau xy, and then let me remove this. We do not need this dimension for the time being. So, we have sigma yy and then tau xy. Okay. Now, let us consider a plane which is passing through this element. So, let us consider a plane. How this plane will be defined? So, it will be defined by the normal. So, let us draw the normal. And as usual, we define this as n. So, we have normal stress which is sigma n, and we also have a shear stress acting in this direction which is tau n. Also, let us define the angle. So, this angle is alpha. Obviously, this angle is also alpha. That means, alpha is the angle that the plane makes with positive x axis. Okay. Now, the question that we are going to answer is estimate sigma n and tau n. Why we need these two components, that I will explain in a minute, but first, for the time being, if we consider a plane alpha defined by its normal n, then let us try to find out what will be the sigma n and tau n, that is the normal stress and shear stress acting on that plane. For that, let us mark the corners. So, we consider this point C. So, ABC is basically the wedge that we consider. So, consider ABC, right. Let the cross sectional area of the side AB be A naught, right. Okay. So, what we can do now, we can identify the forces acting on the wedge, and then we can apply the equilibrium condition, because over this wedge ABC, all the force components acting over this wedge must balance each other, and using that condition we can find out say sigma n. Let us see how we can do it. So, the forces acting on AB are basically one caused by this sigma xx and then tau xy, right. Similarly, what are the forces acting on BC? One caused by this sigma yy and the other one is by tau xy. Obviously, we are considering the lower half of the wedge. Now, if we draw the forces acting on this wedge before we invoke equilibrium equations to solve this problem, right. So, let us quickly draw so that's A, B and C. So, on this face we have the first force component is sigma xx times A naught. Then shear force acting. So, this is tau xy times A naught. Then on this face we have sigma yy, then the area of this face BC is, if this is alpha, so this is A naught tan alpha, and then this one, the shear force is tau xy A naught tan alpha. Then we have along this perpendicular direction we have sigma n, then A naught sec alpha, and this component is tau n A naught sec alpha. So, we have two equilibrium conditions, one along this perpendicular direction n and another is along this direction orthogonal to n. So, the first condition let us satisfy. So, all the forces acting along n is equal to 0. So, if that is the condition, let us see what we get. We have the first component sigma n, then A naught sec alpha, then a component of this y sigma yy will be acting along n. So, that is in the reverse direction. So, we have sigma yy A naught tan alpha, a component of that. So, we can figure out that component. So, this angle is alpha, obviously this angle is also alpha. So, the component along perpendicular n is the sine component. So, this will be sine alpha. Then let us consider this shear force. So, minus tau xy A naught tan alpha, and then this is also alpha. So, we will take the cos component. So, this is cos alpha. Then we have sigma xx times A naught. So, minus sigma xx times A naught, then cos alpha, and then minus tau xy times A naught, and we have to take sin alpha, which is equal to 0. So, we can cancel A naught here, and then we get sigma n is equal to, we take all these components on the right hand side. So, we have the first component sigma xx cos square alpha, because we have sec alpha here, then plus sigma yy, then cos alpha will be cancelled. So, we will have sine square alpha. Then we have the first term plus tau xy, first term will be sine alpha cos alpha, and then plus the remaining term is also tau xy sine alpha cos alpha. We can simplify this. What we have, sigma xx cos square alpha plus sigma yy sine square alpha, plus we can take 2 here, because 2 sine alpha cos alpha is sine 2 alpha. So, tau xy by 2 sine 2 alpha. So, we get the first expression of sigma n, right. So, that is the expression of sigma n. We can consider the remaining direction perpendicular to this n, and we can again satisfy the equilibrium condition, which will give us tau n. That we will do in a minute, but for the time being let us first look at this expression. We can further actually simplify this expression, that we will do in a minute, because we can express cos square alpha and sin square alpha in terms of cos 2 alpha and sin 2 alpha. That we will do in a minute. So, this entire expression will further modify and we will see how does it look like. But before that, let us complete the exercise. So, we have this first expression. So, sigma n is equal to sigma xx cos square alpha plus sigma yy sin square alpha plus tau xy sin 2 alpha. Okay. So, we can take the orthogonal direction along this. So, we call it say n prime. So, this is say n prime. Now, along this direction again we have to identify all the force components. So, the first one obviously very simple. So, it is tau n a naught, then sec alpha. Now, let us find out what are the components acting along that. So, first we consider this normal force sigma yy a naught tan alpha. Okay. So, it will be minus because it is acting on the reverse direction. So, sigma yy a naught tan alpha, and the component of that is cos alpha. Then we have another normal force sigma xx a naught. So, that is acting along the positive direction of n prime. So, we have sigma xx a naught and then sin alpha. Then we can consider the last two components of the shear force. So, we have tau xy a naught tan alpha, and a component of that is acting along prime direction. So, we have tau xy a naught tan alpha, and its component will be sin alpha. The last one is again tau xy a naught, and this is cos alpha, and because it is acting in the negative direction, we put negative sign. Again we can cancel all the a naughts in this equation. So, what we will get is tau n is equal to tau xy cos square alpha minus tau xy sin square alpha, and then we have minus sigma xx sin alpha cos alpha, and then plus sigma yy sin alpha cos alpha. Again we can simplify this expression. We have sin alpha cos alpha here. So, we can write it minus sigma xx minus sigma yy by 2 sin 2 alpha, and then plus tau xy within bracket cos square alpha minus sin square alpha. So, that will be cos 2 alpha. So, we have the expression for tau n also. So, the expression for tau n is equal to minus sigma x x minus sigma y y by 2 sin 2 alpha plus tau x y cos 2 alpha. Now, let us simplify the first expression. So, if you recall, cos square alpha is equal to half 1 plus cos 2 alpha, and sin square alpha is equal to again half, for sin it is 1 minus cos 2 alpha. Now, using these two expressions, we can further simplify the expression for sigma n, and if we do that, we will get this expression sigma x x plus sigma y y by 2 plus sigma x x minus sigma y y by 2 cos 2 alpha plus tau x y sin 2 alpha. So, this is the first equation and we have second equation. So, these are the two most important equations we have in case of 2D stress field. Now, what is the outcome of this discussion? If we have a stress field defined by what? Sigma x x, sigma y y and tau x y. Obviously, we are in 2D. So, the 2D stress field is defined by two normal stresses and one shear stress. Then, if we consider any angle alpha with respect to positive x, then we can easily find out what is the value of sigma n and tau n. Now, if we change this direction, we can find out the normal and shear stress acting on any plane passing through this wedge. So, with that logic, if I extend it to the design problem, if you recall in the last class we discussed that when we design a structure, our main aim is to select a material which has sufficient strength, right. Obviously, in this case we have to select a material which will offer sufficient strength against normal and shear stress, which is governed by this angle alpha. Let us consider first a few special case and then we will further discuss on this issue. So, special case, alpha is equal to 0 degree. So, if alpha equal to 0, obviously cos alpha is equal to 1, sin alpha is 0, cos 2 alpha is again 1 and sin 2 alpha is equal to 0. So, for this case, what is the value of sigma n? We simply put the value of alpha in equation 1. So, what we have if we consider this expression. So, first term cos alpha is 1. So, cos square alpha will be also 1. So, we will have sigma x x. Second term sin alpha is 0, sin square alpha is also 0. So, we will have no component of sigma y y. Then sin 2 alpha is also 0 and there will be no component of shear stress, and which is logical because the plane for alpha equal to 0 is defined by its normal, which is along the positive x, and we have only sigma xx acting along that direction. Now, what about tau n? For tau n, we come to the equation number 2. So, what we have here is sine 2 alpha, which is 0, and there will be no component of axial stresses acting on this differential element. So, we will be only left with tau x y, which is again logical, because that is the shear stress acting on this plane, which is defined by angle alpha. So, our derivation is okay with this proof. Now, let us again investigate for a different angle. So, let us consider 90 degree. For that, let us see what happens. So, for 90 degree, cos alpha will be 0, sin alpha will be 1, cos 2 alpha is minus 1, and then sin 2 alpha is 0. So, you have cos alpha 0. So, the first component here from sigma xx is 0. However, sin alpha in this case is 1. So, sin square alpha is also 1, and we will be having this component sigma yy. Last term sin 2 alpha is again 0. So, we will have no component from the third term, which is again logical, because for alpha equal to 90 degree, it is the direction y as per our reference axis, and therefore, along this direction we have only sigma yy acting, and that is what we get from this derivation. Then again, for alpha equal to 90, sin 2 alpha will be 0 and cos 2 alpha will be minus 1. So, we will have tau, which is actually tau x y with a negative sign, simply because if you recall our sign convention, we consider a case where the plane is defined by its positive normal and also the stress is causing moment or rotation in the positive direction of the x axis. Now, so what we get is that our derivation is as per expectation, and we have sigma n and tau n are actually acting over the plane defined by this alpha. So, what we can do? We can rotate this plane, and for every value of alpha we can solve. So, let us take a problem and then we will see how the normal and shear stress behaves on an arbitrary plane in case of 2D. So, this is the first example in this lecture. So, we have case, and the values of normal and shear stresses are given. Find sigma n and tau n acting on a plane at an angle 45 degree with positive x axis. So, we have sigma xx is equal to 20, sigma yy is equal to 16, tau xy is equal to 8, and alpha is equal to 45 degree. That means, we consider this angle 45 degree. Okay. So, recall what we have derived, sigma n is equal to sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 cos 2 alpha plus tau xy sin 2 alpha, and then tau n is equal to minus sigma xx minus sigma yy by 2 sin 2 alpha plus tau xy cos 2 alpha. Okay. So, normal stress sigma n will be equal to 20 plus 16 by 2 plus 20 minus 16 by 2 cos 90 degree plus 8 sin 90 degree. So, what we have is first term 20 plus 16 by 2. So, this is 18 plus second term, because cos 90 is 0. So, this will be 0 plus 8. So, sigma n is MPa. Shear stress tau n is equal to minus 20 minus 16 divided by 2 sin 90 degree plus tau xy, which is 8 cos 90 degree. Obviously, the first term 20 minus 16 by 2. So, this is minus 2 sin 90, which is 1, and cos 90 is 0. So, our tau n is minus 2 MPa. So, we have found out the normal stress and the shear stress acting on a plane where alpha is equal to 45 degree. Now, that clearly tells us how we can find out different stresses acting on a particular plane defined by the angle made by this plane with positive x axis. So, we will continue on this problem and we will see how further this information helps us to find out the plane over which these stresses becomes maximum. What we will do, we will change this value of alpha, we will start from 0 and then we will go up to minus 180 degree. That means, we will have a complete rotation, and then for all these different values of alpha, we will find out sigma n, and we will study how sigma n and obviously tau n behaves as we rotate the plane with respect to x axis, and how that helps us in our design. That we will discuss in the next class. Thank you very much.